to start off the day by doing a multiple choice question here. I'd like you to take a look up at the board here. Question 96 in your booklet asks you to find a ratio of the radius of an alpha particle's path to the radius of a proton's path. Let's see what you can do with that. Don't bother submitting that one. We'll just do this one and take a look at it as a class in about 3 or 4 minutes. Okay, see what you can do here now. So a proton enters a magnetic field at a right angle to the field. This is good news. Okay, we almost always see it at right angles because we know when it's at a right angle that the equations that we've learned apply. We know that the hand rules that we've learned apply. It's all good. Now, the only other situation that we could see is if it entered parallel. If it's parallel, the magnetic force is 0 and it's not going to go in a circle. Then you don't really have a question. So it's just about has to be perpendicular, but at least they're telling me that so that at least I know that the stuff that I've learned is applicable here. The proton enters the magnetic field perpendicular to the field. The alpha particle goes the same field, also perpendicular to the field. Once in the magnetic field, both particles move in a circular path. We don't need to be told that because we know that's what's going to happen. The question here is, what's the ratio of the radius of the alpha particle's path to the radius of the proton's path? So in other words, we're looking for this. The ratio of the alpha particle's path to the proton's path. Careful, we're not looking for this. There's a difference. There's a difference. Okay, if we say the ratio of my age to your age, it's about 2 to 1. If we talk about the ratio of your age to my age, it isn't 2 to 1 because you're not twice as old as I am. The ratio in that case would be about 1 to 2. There's a clear difference here, okay? I'm either twice as old as you or I'm half as old as you. That's a difference. So this one we're looking for, the ratio of the alpha particle's path to the proton's path. So let's go at it from that angle here. Hey, what do you think when you see the word ratio? We saw something like this not very long ago, just a few days ago. It wasn't the word ratio, but it was almost the word ratio. We wanted to compare two things a few days ago. You remember that? What do we do when we compare two things? Same thing we do when we want to find a ratio. But what is that? Divide. So which one are we going to divide? R alpha by R proton? Or is it going to be R proton by R alpha? Which one is it? It matters, right? Is it my age divided by your age, or is it your age divided by my age? Which is it? We're looking for R alpha to R proton, so it's going to be this one, right? Now, if we've got the value of R alpha and R proton already, it's easy. Just divide the two numbers, got a ratio between the two, done. But we don't know what R is, so let's find it. We know that FC is equal to FM. We know that MV squared over R is equal to QVB. These cancel. I know that R is equal to, what, MV over QB? Oh, perfect. Let's plug my numbers in here, find the radius of both of those paths. Let's divide the two. We're done. Problem is, I don't know what speed is. I don't know what magnetic field is. I do know what M is and what Q is from my data sheet, but I don't know what V or B is. So I can't find the radius of the alpha particle's path or the radius of the proton's path. So what I'm going to do is the same thing as I did the other day when I did a question like this. I'm going to sub in some expressions. I'm going to say M alpha, V alpha over Q alpha, B alpha, divided by M proton, V proton, over Q proton, B proton. Okay, it looks kind of ugly, but the good news is things start canceling out here pretty quickly. It says the magnetic field is the same, so magnetic field will cancel. Done. It says the speed is twice the speed. We don't know what the speed is, but we know the alpha particle is twice the speed of the proton, so we can sub in 2V in for the speed of the alpha particle. That means that VP can cancel out. Now, at this point, you can plug in numbers for M and Q for both of those particles, or take a little shortcut. If you recognize that the mass of the alpha particle is 4 times the mass of the proton, and you can see that on your data sheet, then MP also cancels. If you can see that the charge of an alpha particle is also twice the charge of a proton, then QP cancels. Now, you don't have to spot that. Okay, and if in the end you don't spot that, you can plug in the value for charge of the proton, charge of the alpha particle, mass of the alpha particle, mass of the proton, and so on. But if you do spot that, look, just about everything cancels out. I'm left with 4 times 2 divided by 2, it's just 4. What's the ratio of the alpha particle's path to the proton's path? 4 to 1. Does that make sense? How many people got that? Good, not bad. Not bad at all. Let's spend a couple quick minutes reviewing what we've been doing over the last couple of days, and then we'll do a couple multiple choice questions, or numeric response questions it is, on that. And then we'll do some new stuff here to finish off the unit today. Remember, guys, if we've got a moving charge, what direction is the moving charge in this case? Represented by an X. It's going into the page. So let's say we've got an electron going into the page. If we've got an electron going into the page, it produces a magnetic field. The magnetic field produced by it would be clockwise like this. We'd find it by the wire grasp rule. Thumb, fingers, wire grasp rule says, did I say clockwise? Should have said counterclockwise magnetic field, right? If I've got a couple magnets here producing a magnetic field, okay, that magnetic field is going to be from north to south. You get 2 magnetic fields, and they interact in kind of a strange way here to produce a magnetic force that's perpendicular to the direction of motion of the particle. You're going to say thumb in the direction of the particle, fingers in the direction of the external field from north to south. Palm's going to point towards the right side. So we're going to have a magnetic force on that moving particle towards the right side of the page. Now, if that particle is inside a wire, it will also experience a force toward the right side of the page. If there's 1,000 of them inside of the wire, then 1,000 of them are going to experience a magnetic force toward the right side of the page. Normally, each and every one of those electrons traveling into the board would want to travel in a circle. But in this case, they can't travel in a circle because they're held in place by the wire. The wire physically keeps them from moving in a circle. So instead of the electrons moving in a circle in this magnetic field, because they're held in place by the wire, the electrons will drag the wire along with it when they experience the force to the right. So not only do the electrons move to the right, Abby, but the wire that the electrons are carried by will also move to the right. There's a magnetic force on the charges and a magnetic force on the wire that carries those charges. Now, we find the direction of the force in the exact same way. It's the hand rule for deflection. But we find the magnitude in 2 different ways. The magnetic force on the charged particle is QVB. The magnetic force on the wire itself is ILB. The current times the length of the wire times the magnetic field strength. All right? Now, we've done a few questions involving this F is equal to ILB. This is our newest thing, right? F is equal to ILB. Done a few questions on that. We did an activity on Tuesday on that as well, activity that's due tomorrow. What I want to do right now is take a look at a couple multiple choice questions that involve this. So without further ado, let's take a look at multiple choice number 85 and 86. Don't bother submitting these, the numeric response questions. Please do them at your desk, though, together. And then in a couple of minutes, once you finish them, we'll take a look at them as a group. Number 85 says a 50 centimeter length of wire, and we want to draw attention to the centimeters, right? Has a weight of 0.389 newtons and a current of 0.250 amps. The wire remains suspended. That's a key word too, right? Suspended. What does that tell us? I like it when we see that word. I like it when we see keywords like that in general because they kind of tell us what to do. There's a lot of questions where you kind of just got to think on the fly, what am I going to do with this question? It's kind of hard. Okay, when they tell us something's suspended, they're telling us what to do. What do we do? Good. If it's suspended in a magnetic field, then that magnetic force, not the magnetic field, the magnetic force will equal to the gravitational force. Now, the magnetic force on a charged particle is QVB. On a wire, it's ILB. Now, the gravitational force is M times G. But you know what? We already have the gravitational force here at 0.389. The weight of the object is the gravitational force. So in this case, we got I, we got L, we have the gravitational force. We're just going to solve for the magnetic force here. 0.389 divided by I times L. And it seems to me we get 1 point something. 1.07, does that ring a bell? All right, let's try that again. 3.11 Tesla. Now notice how they want that to be expressed. It doesn't say scientific notation. It's not B times 10 to the W. It's not A decimal BC times 10 to the D. It's just, hey, what's the strength of it? When you see a blank that looks like this, you should expect to get a pretty normal number, not with exponents, right? If you get 10 to the 4, or 10 to the 7, or 10 to the minus 2, you've made a mistake because you can't express that in standard notation, and that's the way they're asking me to express it in standard notation. So we'd simply express this one as 3.11. Is that okay? Okay, second question says, a wire that is 75 centimeters long, again, centimeters, carries a current of 6 amps. The wire's at right angles again. Okay, that's good. Experiences a magnetic force of 0.350. What's the field? This is really straightforward, right? We're going to say for this one, F is equal to ILB. We're looking for B. So as long as you can rearrange it correctly, we should be able to nail this question here. The force is 0.350 divided by the current, which is 6 amps, times 0.75 meters long. What do we end up getting for that one? 7.78 times 10 to the minus 2 Tesla. How do I know that you're probably in the right range there? How do I know that it's not 7.78 times 10 to the positive 3? It would be way too big. Yes, that's a good point. It's not what I was thinking, but you're right. It would be way too big. Yeah, they actually tell me it should be a negative exponent there. I like it when they do that as well. Okay. It doesn't mean that because I got a negative 2, it doesn't mean that I'm right, but it does mean that if I get a positive 1, then I'm wrong. So sometimes when I make a mistake on this question, they're going to tell me I made a mistake by telling me that it should be a negative exponent. So how do we express that? We're just looking for the value of B. This is not an A decimal BC times 10 to the D. So we're going to express that as 778, right? Not the 2. Is that right? No. Parker, how do I express it then? Good. If it was A decimal BC times 10 to the D, 7782. B times 10 to the W, 7.78. All right. Let's switch gears and talk about a new concept, which is going to go pretty quickly for us, but still a new concept, called the generator effect. Physics is a very symmetrical subject. When A causes B, then a lot of times B will cause A. We learned a couple weeks ago that electricity generates magnetism. A discovery made in 1819 by a guy named Hans Christian Ørsted. When you have an electric current, it will make a magnetic field. So maybe, by symmetry, a magnetic field will also generate an electric current. Well, it turns out it does, at least sometimes. That discovery was made in 1831, not very long after Ørsted's discovery was made, really. 12 years later. Was made independently by a couple of guys, an Englishman and an American. If electricity generates magnetism, then magnetism can also generate electricity. Now, there's conditions on this, and we'll talk about those conditions in a minute. There's not conditions on the first discovery. Electricity will always generate magnetism. Magnetism will sometimes generate electricity. But we still have some symmetry involved there. Why does that happen? Well, I'll give you a little bit more detail on that in just a moment here, but for now I'll refer you to the paragraph there. Basically it says, look, it happens because when we move a wire through a magnetic field, we end up, believe it or not, generating a magnetic force on electrons in the wire. And that magnetic force causes the electrons in the wire to start moving. So what we're really doing here is, fundamentally, of course, we're generating an electric current by moving a wire. But why is that happening? It's happening because we're producing a magnetic force on the electrons within the wire. And because of that, they start moving through the wire and generating an electric current. What are the conditions under which this happens? We said that electricity generates magnetism, always. Magnetism sometimes generates electricity, but there's conditions attached to it. Well, there's a couple of conditions. Okay, first one, you always have to have a magnetic field, okay, an external magnetic field, and you always have to have a conductor, a wire, we'll say. So you got a wire and a magnetic field. Now, in order to generate an electric current, you can't just have them sitting beside each other. You have to move one of them. Doesn't matter which one you move. Move the wire through the magnetic field, move the magnetic field around the wire. Doesn't matter. You're going to generate an electric current in the wire in both cases. But one of them's got to be moving. Both of them could be, excuse me, both of them could be moving relative to one another. But in the end, all you need is one of them to move. You need relative motion. Or change the value of the magnetic field. Change the strength of the magnetic field. I should have said, actually, you still need a wire and a magnetic field, not just the magnetic field. You need the wire and the magnetic field, but you can change the strength of the magnetic field in addition to moving the magnetic field of the wire. That's also going to generate an electric current in the wire. Take a look at a diagram here that's going to help us to understand why there's a current generated in the wire, why we produce electricity from magnetism. You can copy this down if you want or not, doesn't really matter, as long as you understand what I'm saying with it. And it boils down to the paragraph that you wrote down on the last page. First diagram over here. Let's scratch this out. Let's scratch this out. Let's scratch this out. Hey, all we have now is a wire with electrons in it, of course, because a wire always has electrons in it, just like your desk always has electrons, just like your hand always has electrons in it. Okay, there's electrons in a wire that's just sitting there in an external magnetic field. Now, this wire presumably is copper. It's not ferromagnetic, so it's not going to be attracted to one of the poles or the other. It's not affected in the slightest. You've got stationary electrons in an external magnetic field. Okay, it's just like you standing along the Earth. Okay, the Earth's magnetic field is there. It's surrounding you. You're not moving. Nothing's happening. Okay, the Earth's magnetic field doesn't affect you. But watch what happens when I push the wire upwards. Now, I may push the wire upwards by my hand, or maybe I burn coal, generate a lot of heat, boil water, create steam, and the steam rises and pushes the wire upwards. Or maybe I split the atom, and the atom splitting generates a whole lot of energy, boils water, creates steam, steam rises, pushes the wire upwards. It doesn't matter how I push the wire upwards. If I push the wire upwards, all the electrons inside the wire are also being pushed upwards. So now, you not only have a moving wire, although it's not a moving wire because of a magnetic force, it's a moving wire because you pushed it. You also have electrons inside the wire moving. Let's take a look at what's happening now. If these electrons, let's look at one individual electron. If this one individual electron is moving upwards, doesn't matter why it's moving upwards, it's moving upwards. We can stick our thumb in the direction of that moving particle, it's upwards. Our fingers in the direction of the magnetic field, which is north to south. That causes a magnetic force on that electron and on all other electrons in that wire to be out of the page. So think about that. We've just produced a magnetic force on the charged particles within the wire out of the page. What happens to those electrons now? Well, they start moving because they're fairly free to move about, right, in a conductor. So they start moving out of the page. Well, what do you call it when electrons are moving through a wire? It's called an electric current. So by simply pushing the wire upwards through this magnetic field, we've caused a magnetic force on the particles within the wire, and we've caused those particles to start moving. We've caused an electric current just by moving the wire through a magnetic field. This is the basic principle behind just about every bit of electricity generation that we use on the grid, okay, that comes to our houses and comes to businesses. Most of the energy, most of the electricity in Alberta is generated by burning coal. Burn coal generates a whole lot of heat, boils water, creates steam, steam rises, turns a turbine, which is effectively pushing this wire upwards through a magnetic field. Electricity starts flowing. Okay, another way we generate electricity, hydro dams. Not so much in Alberta, but in Ontario they do this a lot. Quebec, Labrador. Okay. Water, lots of places in the United States, water gets held up behind a dam, has a lot of gravitational potential energy. It falls down through this tube, down through this penstock, okay, turns a turbine, which is basically, turns a turbine, pushing a wire through a magnetic field, generates an electric current. Wind power is becoming big in Alberta, especially southern Alberta. Okay, what happens? Well, the kinetic energy from the wind causes the blades of this turbine to turn. When the blades of this turbine turn, well, it moves a wire along with it through a magnetic field, generates an electric current in the wire. Even nuclear power. Split the atom. When the atom splits, it generates a whole lot of energy. That energy boils water, creates steam. Steam rises, moves a wire through a magnetic field, turns a turbine, moves a wire through a magnetic field, generates an electric current. So just about everything that sends power to our houses is based on this principle. We call it the generator effect, because we're generating electricity by moving a wire through a magnetic field, or you could do it the other way around by moving the magnetic field through the wire or around the wire. Same effect there. Okay, the only kind of widespread electricity generation that sends electricity to our houses that I can think of that isn't based on this principle would be solar power. Okay, it's based on a completely different principle than moving a magnet or moving a wire relative to each other. And even that, as I said, widespread, that's not even widespread, right? We don't generate a whole lot of power by solar power. Okay, that which is generated by solar power is usually on the roof of somebody's house, not on some farm somewhere, some solar panel farm somewhere, sending it back to the grid. Okay? Usually the electricity that's on the grid is generated by this. Does that make sense? We got some questions on page 613 that you're going to have for homework. But since you have an assignment due tomorrow and a lab due tomorrow, we're going to make these questions due on Monday. The questions that I want you to work on are on page 613, number 1 to 3, and 7 to 11. You might have a little bit of time towards the end of the class to work on these because things seem to be going pretty quickly for us here today. The demonstration that we just did with a copper tube, the piece of steel, and the magnet demonstrates this phenomenon called Lenz's law. It's a nice way to end the unit because it kind of ties together a couple of concepts, a couple of pretty major concepts that we've done in this unit. The first one is the concept that we just did a few minutes ago, and that is electromagnetic induction. We can generate an electric current by a magnetic field. Now, how do we do that? I told you there was 2 conditions, one of which had to be met. You got a wire, you got a magnetic field, you got to move one of them. That's the condition that we're looking at here. I had a magnet for Kirsten and Ryan when they were dropping the steel through the copper tube. The piece of steel was actually a magnet. Now, it's not attracted to the copper, but as that magnet moves through the copper tube, what happens? Well, we generate a current. That's Faraday. That's Henry. That's what we just learned, right? If you got a conductor and a magnetic field and you move one of them, then you're going to generate an electric current. It's not new. Well, it is pretty new because we just learned it today, but it's not brand new. You got a magnetic field, you got a wire, you move one of them, you generate a current. It's electromagnetic induction, just the same as when we split the atom and generate heat and boil water and create steam and turn a turbine, exact same thing. Now, the current that's generated would be in the copper tube. It's a small electric current. We're never going to feel that electric current. I can hold the copper tube when Parker or Kirsten or Ryan was dropping something through the copper tube, and it's not going to hurt me. I'm not even going to notice that there's an electric current there, but there is a current there. Now listen very carefully to what I'm about to say. There is an electric current now in the tube. It wasn't there before. It's there because I moved a magnet through it. But there's an electric current there. The electric current generates a magnetic field. We learned that weeks ago. Hans Christian Ørsted, 1819, said electric current generates a magnetic field. Still nothing new. But we got 2 magnetic fields here now, right? We got a magnetic field that generated an electric current, and then we have an electric current that was caused by the magnetic field that produces another magnetic field. We have our original magnetic field that we started with, that we dropped through the copper tube. We have a new magnetic field that was produced by the electric current that was produced by the original magnetic field. Now we get two magnetic fields. Those two magnetic fields will always act together to oppose the motion of whatever it is that's moving. So if I drop a magnet through a copper tube, we're going to produce an electric current, which is in turn going to produce a second magnetic field. The original magnetic field, that is the magnet that I dropped, and the new magnetic field that was produced there will oppose the motion of the magnet. Now, why do they oppose the motion of the magnet? Well, when you get two magnetic fields, they have to interact. They have to cause a force. Why can't it be an attractive force? Why can't they help the motion? Why can't they cause the magnet to speed up at a rate greater than 9.81 meters per second squared? Because it would violate the law of conservation of energy. If the magnet starts at a certain height with a certain amount of potential energy, it can't have more kinetic energy than that when it reaches the bottom. But yet, if it sped up at a rate greater than 9.81, it would have more kinetic energy than potential energy at the top. It just can't happen. You can't create energy from nothing. So if there's going to be a force, and it can't cause the object to speed up at a greater rate, well, then it must be causing the object to slow down, or at least speed up at a smaller rate. A magnetic field generates a current. A current generates another magnetic field. These two magnetic fields act together to oppose the motion. The little trick with Parker was he was dropping a piece of steel, right, not a magnet. It fell at 9.81 meters per second squared. Why? Well, because when you drop the steel through the copper tube, it didn't generate a current. And if it didn't generate a current, you're not going to get a second magnetic field. And if you don't have a second magnetic field, you're not opposing the motion. When Kirsten dropped the magnet through the copper tube, the magnet that looked exactly the same as the piece of steel, what she was dropping wasn't sticking to the copper tube because it's not ferromagnetic. But it was generating a current, which in turn generated another magnetic field, which, along with the original magnetic field that Kirsten dropped, opposed the motion of the magnet. The same thing would happen, by the way, if I somehow held the magnet in place and dropped the copper tube. Now, that's a more difficult one to do, right? Because how do you hold the magnet right here and then drop the copper tube around it when you still got your fingers on the magnet? But if you could do that, you would notice the copper tube falling, even accelerating, but accelerating at a rate that was less than 9.81 because its motion would be opposed by the two magnetic fields. That make sense? There's a couple questions on your assignment that are actually related to this. You're not going to see a ton of questions on your unit test on Tuesday, sorry, for you guys on Wednesday, on this, but you'll see one probably, kind of like one or two of the questions that you see on your little mini assignment. Basically, summarize any of the questions that you could see on this. Let's say we've got a magnet. Let's make it north and south. And let's say we've got maybe a coil. Maybe we've got another piece of steel in there. It's not magnetized. We've got a coil of wire right here. Instead of having a battery down here, we've got a light bulb down here. That's a symbol for a light bulb, by the way. This light bulb isn't on, right? Because there's no battery hooked up to it. But if I move this magnet towards this coil of wire, then we could actually generate an electric current and conceivably turn on this wire or turn on this light bulb. First of all, my question is, what's the polarity of this coil? And second of all, what's the direction of the current? What's the polarity of the coil? Well, we know as we're moving this magnet nearby the coil, the motion has to be opposed. So tell me right now, what's the polarity of this coil if it's going to oppose this? Well, this has got to be south and this has got to be north, right? If this was north, what would happen? It wouldn't oppose it. It would pull it towards it, right? It would help its motion, not oppose its motion. So that's got to be south, and that's got to be north in order to oppose the motion of that moving magnet, right? Well, how do we find the direction of the electric current in there? Well, we're going to use that coil rule kind of in reverse. Instead of saying, hey, stick your fingers in the direction of the current, thumb in the direction of the magnetic field, this time we're going to say thumb in the direction of the magnetic field. Remember, inside the coil, it's going from south to north. So we're going to stick our left thumb towards the north. Our fingers will point up in the front. Lo and behold, the electric current will go up in the front and then down in the back and around like this clockwise. Does that make sense? So it's kind of what we did early on in this unit with the coil rule. But it's also this thing that we learned today with Lenz's law. In order to do this, we had to know the polarity of that coil. And the polarity of that coil came from the moving magnet. Okay, the moving magnet is pushed towards it. That coil has to oppose its motion. And the only way to oppose the motion is to have a south pole against a south pole. Does that make some sense?